Good afternoon, everyone. Thank you for joining this afternoon's webinar, Monitoring Construction Vibrations, given by Steve Moore, professional engineer and senior engineer at Atlantic Testing Laboratories.
So general outline, construction vibrations. We'll talk about different types and characteristics of vibrations, specifically construction vibrations, the human and structural response of construction vibrations. We'll talk about some vibration monitoring equipment and the setup, and we'll talk about some of the different vibration recording modes and some of the pros and cons of those different recording modes. Then we'll get into talk about some of the thresholds, some industry specifications, thresholds, alerts, limits. We'll talk a little bit about New York State DOT specification 634, 9901, 9902, and we'll talk a little bit about condition surveys, which are part of the that DOT standard specification or special specification. It's actually not a standard specification. So construction vibrations, I'm going to use my mouse here to point out some things since I don't have a laser pointer. Different wave types and energy transmission. So we've got compression waves, those are P waves. There's some compression and tension with those waves. You can see some tension in here and compression in here. You can think of that in some ways as like traffic moving down a highway. You know, you get to a traffic jam and you know the cars start to bunch up, and then traffic opens back up again and they start to separate. You know, there's a good analogy for kind of the compression and tension on those P waves. S waves or shear waves. You get vertical, kind of that vertical side to side or up and down shearing of the particles, adjacent particles. And then you've got surface waves or rally waves, and you kind of think of these as maybe like a bobbing cork, you know, kind of almost rotational bobbing cork on the surface of water. There's a certain amount of compression and tension involved in these rally waves also. But something to point out here, these rally waves, the surface waves, most of the energy is transmitted through these surface waves, through these rally waves. So about 2/3 of the energy is transmitted in those surface waves. So those are really the ones that come into play most of the time when we're monitoring construction vibrations, and it's those surface waves that travel along the surface of the ground. There's usually two main types of vibrations or vibration classes. Maybe you can think of it that way. Steady state vibrations, they're more continuous, greater than 60 seconds. You know, these are like your, sheet pile installation, vibratory compaction, rock sockets. And these are the ones that are a lot of times classified as a little bit more annoying. You know, they're persistent, they last a long time, and you know, they're just more annoying. These transient waves, sometimes kind of a single event blasting. They've got a single peak. They last less than 5 seconds, usually on the order of 1 to 5 seconds. A little less annoying. But you know, if anybody's ever been around pile driving, it's considered a transient events. Each one of those impacts is a transient event, but certainly plenty annoying if you've been around it long enough. So we got a little bit of a gap in here between the steady state and the transient. You know, steady state being continuous, 60 seconds or more, transient being that 1 to 5 second impulsive type thing. What about those vibrations that last somewhere in between, 5 to 60 seconds? Some people call those kind of a quasi steady state. but certainly no less annoying than the transient ones. So ground vibrations, characteristics, the three main characteristics: frequency, amplitude, velocity. I will say that whenever we're talking about construction vibrations and analyzing construction vibrations, we look at this as a very simplified model. Vibrations in general can be very, very complex. How they're transmitted, the receiving points, how they're processed. But generally speaking, just to make things easy, we use kind of a simplified model, like a sine wave. So you've got your frequency, amplitude, which is displacement, and the velocity. And in this case, we're talking about particle velocity, not wave velocity. Those are a little bit different, but in this presentation, for the most part, anytime we talk about velocity, it's going to be an individual particle velocity. So frequency, I think we all know what it is. It's a cycles per second, typically measured in hertz. Time for one cycle is a period. Frequency is the inverse of the period. The period is the inverse of the frequency. And again, for simplicity, most seismographs use what's called the zero crossing method when we're processing frequencies and amplitudes and velocities, and I'll show that in a diagram a little bit better as we go along. Amplitude, in our case, the amplitude is the displacement. It's the distance that a particle moves. And this is very important for damage assessment, although typically in construction vibrations, we're measuring the velocity, but we can figure out the amplitude from the velocity, just dividing the velocity by 2 pi times the frequency. Velocity, again, particle velocity, not wave velocity. If anyone's ever been to a big sports stadium, most likely not recently, but in the past, and people in the crowd, they do the wave. Everybody stands up and sits down, and that wave kind of travels around the stadium. You've got a wave velocity, which is the velocity of that wave traveling around the stadium. But again, that's not what we're looking at here. We're looking at the particle velocity, and think of that as the individual fan in the stands, standing up and sitting back down. That's the individual particle velocity that we're looking at and that we're going to be talking about throughout the presentation. It's typically measured in inches per second in the US, millimeters per second pretty much everywhere else in the world. And again, simplified sine wave, 2 pi times the frequency and the amplitude for the velocity. I've got this diagram just to kind of show you the different, different wave fronts when you're driving a pile. Down here at the bottom, at the toe or the tip of the pile, you've got these spherical body waves that go out again, in a sphere throughout the shaft of the pile. You've got these body waves that kind of travel in more of a cylindrical wave front. And then here at the surface, that's where we've got those rally waves. And again, these are the ones where a lot of energy is transferred. And one thing I'll say, all of the vibration monitoring that we've done, most of the time you get your peak particle velocities. Like if we're monitoring for pile driving, you get your highest peak particle velocities right after the first couple of blows, or right at the first couple of blows of the hammer, when the pile is right at the surface. And if you think about it, taking a look at this image, if you think about it, none of those body waves are really present because you don't have any of that shaft, or very little of that shaft, in the ground. the toe is pretty much right at the surface. So that's really where you're getting all those rally waves from. And as the pile gets embedded deeper and deeper into the ground, you've got the same amount of energy going into it. That's the pile, that's the hammer hitting the top of the pile. So the amount of energy doesn't change, but that energy is dissipated over more of that pile, the length of the pile and then down at the toe. So more often than not, when we're monitoring vibrations for pile driving, those first few hammer blows, those are the ones that are going to give you the highest vibration readings. And the same is true for sheet piles when installing sheet piles, and using the same analogies. So the human response, it's important to know that it's kind of a qualitative response. Everybody reacts a little bit differently to vibrations, but the human body is an excellent vibration receptor, and we use multiple senses. We use our sense of touch or feel, because we can feel the vibrations to a certain extent. We use sound also. If you're around pile driving, obviously you can hear it. So a combination of feeling, hearing it, and maybe to a certain extent even sight. So multiple senses involved with human receptors. But here we can see some of this is pretty old research. I got this from a Caltrans manual for construction vibrations. But you can see here, different peak particle velocities. Obviously, as the peak particle velocity increases, it becomes much more disturbing and more perceptible. Right around 0.01 inches per second, slightly perceptible. Similar down here, 0.006, kind of the threshold of perception. 0.1 inches per second begins to annoy. 0.1 inches per second, it's strongly perceptible. These are steady state vibrations, so these are the ones that are lasting, more than 60 seconds. That vibratory roller, the sheet pile, vibratory head installing sheet piles. Again, as the peak particle velocities increase, our human response obviously changes. These transient vibrations, those impulsive vibrations, the single impact of the pile hammer, again, 0.035, that's barely perceptible, again, inches per second. 0.9, strongly perceptible, which pretty much coincides. This is research done in 1974, but pretty much coincides exactly with the research that was done, 40 years before that, where 0.9 or 1 inch per second, it was very strongly perceptible. This is a diagram that just kind of gives you an idea of typical vibration, the peak particle velocities at 25 feet from various sources. So 1 inch per second, 25 feet, your impact pile driving, is going to be about 1 inch per second. Vibratory pile driving, less than that, obviously. And it kind of goes down. You see hoe rams down here, jackhammers, bus or truck on a typical city street. That's that 0.01, kind of where it's that threshold of perception down in that area. So we'll talk a little. Those were the human responses. We'll talk a little bit about the structural responses. Something to keep in mind. The structure responds to the ground motion. So it's the ground vibrations that the structure is responding to. These can be extremely complicated. It's going to be unique for the structure itself. based on the materials, is it a steel building, steel frame building, wood frame building, reinforced concrete? Is it a masonry building that may be a little bit more rigid? And those steel frame buildings, they're a little bit more flexible based on geometry also. Round structures are gonna respond differently than square structures. A long structure like a warehouse, a warehouse slab may react differently depending on where the vibration source is coming from, because it's longer in one direction than it is in another direction. But again, that response is due to the ground vibration. We can quantify that sometimes using various single degree of freedom models and assumptions, with spring constants and masses, and we've got the input velocities and input frequencies and stuff like that. It can be quantified, it can be modeled. We are not going to do that today. We're not going to talk about that too much today. Probably the biggest takeaway here with the structural response is every structure has a resonant frequency. A lot of us have probably seen that video from the Tacoma Narrows Bridge, with the wind blowing and the bridge basically collapsing from resonating frequencies from the wind blowing. Each structure, again, has their own unique resonant frequency. It can be determined. We want to make sure that structure is not going to be vibrating at that resonant frequency, or that input frequency, isn't near that resonant frequency. Usually resonant frequencies for structures are pretty low, 6, 8, 10 hertz or something like that. But again, we're not really going to discuss any of that specific structural response beyond that today. So we'll get into the vibration monitoring. We'll talk about some of the different equipment that's used, some of the different types of setups, recording modes. We'll talk about some of the pros and cons of different recording modes. I'll show a handful of different data that we've collected over the years. Again, we'll talk about some of the specifications, industry standards, specifically New York State DOT and the U.S. Bureau of Mines RI 8507 standard, and then we'll discuss some condition surveys a little bit also. So here's kind of where the rubber meets the road here. This is a geophone. This is what's attached to the ground, spiked to the ground, maybe attached to a building sometimes, but something to understand when you're attaching a geophone to a building or to a structure. You're no longer measuring that ground vibration, you're measuring that structural response. So we try to set these on the ground outside of the structure as much as we can. So we're measuring those ground vibrations. Inside a geophone, this is kind of what it looks like. It's got a magnet, there's a coil around it, there's a mass around there where that the coil surrounds. And as this moves up and down, you can see this is going to create a negative voltage and a positive voltage. And that's the output essentially that we get from these geophones is a negative positive voltage, and that's kind of that wiggle trace that you typically see for on a seismograph or something like that. That wiggle trace is really just the varying voltages. In these geophones, they're all pretty much 3-component geophones, or at least all the ones we use for vibration monitoring. They're 3-component geophones. So they've got this setup, this magnet coil setup on 3 different planes. There's one on the vertical plane, there's one on a longitudinal plane, and there's one on a transverse plane. The longitudinal plane is kind of the back and forth towards the vibration source. Transverse plane is perpendicular to that, and obviously the vertical plane is up and down. All of these go into a computer. This analog voltage, this analog signal is converted digitally by a computer. And some of the setups, we're starting to do a lot more remote monitoring these days, where the seismograph is also hooked up to a cellular modem and transmits the data, once or twice a day, maybe at the end of the day. Maybe has got some threshold values set up during the day. So if it reaches a certain point or a certain peak particle velocity, it records that, and it sends out a notification either by email or by text, sometimes both, to some interested parties on the project. So everybody kind of understands that maybe you're getting close to some limits. Something else about the equipment is the setup, and I've got location, and you hear real estate agents all the time. They say location, location, location. That certainly is very important when monitoring construction vibrations. We want to make sure that it's set up properly and really set up in the right location. To have a seismograph set up, right here next to this hole ram, you're certainly going to be measuring the vibrations that this hole ram is producing, but it's not going to tell you anything that's going on, or not a whole lot that's going on in this house back here in the background. Maybe that's the house, maybe that's the structure that we're trying to protect from construction vibrations once they start, driving some piles here for the abutment or something like that. So to set up near this hole ram is really not practical. We want to set up near this house because we want to see what kind of vibrations that structure is seeing, and we want to make sure that we're controlling those adequately. We want to make sure that it's set on firm ground. You got a good solid coupling. Usually what we do is we'll dig a hole maybe about anywhere from 6 to 12 inches deep, maybe deeper. And then we'll set the geophone down inside that hole. We'll pack some dirt around the geophone, and then we'll put a sandbag on top of it again, kind of make sure that we get good solid coupling. It's not slipping around or anything like that. If we don't have the opportunity to dig a hole, we'll attach it to the surface. Maybe it's outside in a parking lot, or maybe it's inside on a floor slab or something like that, and we can attach it directly to the surface. Here's a setup. Here's the geophone. You kind of see the geophone wire going to this hole right here, and that's just a sandbag we've got over the geophone. It's pretty much right at the corner of this building. Taking a look behind me, you can see right here, this is the work that we're monitoring. There's a little bit of demo work going on right here. Here's our seismograph, and the sandbag right here. So we're monitoring demo operations right here later on in the project. They were driving some piles, and we were monitoring that as well. This particular one, it does have inside here, there is a modem that's hooked up to a cellular service. Got a solar panel here to kind of keep everything charged up, although the angle of that solar panel certainly isn't ideal. But that's a fairly typical setup for a remote monitoring situation. Some of the different recording modes that we can use. Waveform recording mode, that's that typical wiggle trace that you see, kind of plots amplitude as a function of time. It's really good for analyzing events. You can take a look and see if this is, is this a transient event? Is it a sustained event? And maybe even evaluate it a little bit more using some other analysis to maybe see what the source is. Histogram recording mode is another mode that we record. It's good for a long-term recording. It's usually, it records over a fixed interval over a long period of time. So we may have a histogram recording in 1 minute intervals. So every minute it records seismic information and then spits out the highest peak particle velocity and frequency within that minute of recording time. And then it goes and records for the next minute and the next minute and the next minute. So you've got a long-term, you've got a long record of data, and you've got vibration data essentially for every minute while it's recording. Another recording mode is a trigger mode. I guess it's less of a recording mode, is just an option to set a trigger value, and the recording will begin when that certain value is reached. So if you've got a threshold value of maybe 0.5 inches per second on a project, maybe you want to set that trigger mode at 0.25 or 0.35 to know if you're getting close to that 0.5 inch per second threshold that's set up on the project. Think of that as maybe your Amazon Alexa that's just kind of listening in the background, but it's not recording anything, and it doesn't start recording until you reach that trigger value. Alexa doesn't start to really give you any information until you say, "Hey, Alexa." So that's kind of the trigger. And then another mode that we use, probably more common than any other one, is the histogram combo mode, which is kind of a combination of the histogram mode and a trigger mode, where it records in histogram mode every minute or maybe every 5 minutes until a certain threshold value is reached, and then it goes in waveform mode, and it records a waveform trace. That way you can analyze, if you've got a threshold of 0.5 inches per second or 0.25 inches per second, and it reaches that threshold, it'll record in that waveform mode, and you can kind of see the characteristic of that vibration. Here's an example of a waveform. And this particular one, we had the trigger set at 0.25 inches per second. So you can see this is a transient vibration. It lasted, less than 1 second, maybe a quarter of a second or something like that, or maybe half a second. And one of the things that these instruments do when it hits that waveform or that trigger and starts to record in waveform, it actually records about a quarter of a second before the trigger. So right here, this is the 0.25 inches per second trigger right here. So this is the amplitude, when it reached 0.25 inches per second and initiated that recording, it recorded the previous 0.25 inches or so, and then continued recording for about 5 seconds. You can see again, this is kind of a transient event, call it an anomalous event, whatever. But a couple other things we look at on these records. Here we've got our 3 different recording planes, right? We've got our transverse, vertical, and longitudinal. I look at the scale here so we can see, it's a little small, but we can see our scale right here is plus or minus 0.4 inches per second. That's the same for all of these. So, we take a look at the scale, just to see, kind of the magnitude of what these vibrations are that are plotted out. And then one of the other things that we look at in this waveform, data is, after this 5 seconds is done, after it's done recording for 5 seconds, it does a self-check for on the geophone in each of these 3 directions: the transverse, vertical, and longitudinal. And essentially what this does is, you've got a voltage, it induces a voltage on the geophone and then releases that voltage. So the magnet goes up, and then when it releases that voltage, we want to see that magnet drop back down and kind of vibrate back to back to a steady state condition. So that's what this waveform is here. Here's the voltage, it releases it, that magnet just kind of travels back and settles back down. And that's done at all three of the all three of those those geophones inside. Here's a record of a histogram. Again, looking at the scale here on the left. The histogram just provides absolute data. It doesn't give the waveform data, that gives, positive, negative voltage. It just gives the absolute voltage, or, in this case, obviously the peak particle velocity. So we can see over here at about, I don't know, just before 1 o'clock, this is when our highest peak particle velocity was throughout the day. These are our individual, this is our histogram interval, and these are 1 minute intervals. So we've got data along here every minute, right up until, just about 3 o'clock, or probably right at 3 o'clock. Again, looking at the scales, here's our longitudinal, L for longitudinal, transverse, vertical, and our scale goes up to about 1/2 inch per second. So, this value over here, we're talking somewhere around, 0.3 something, 0.3 inches per second. This is another histogram event, histogram recording mode. And here it's plotting each one of those 1 minute intervals on the US Bureau of Mines standard. That's this stair-step curve right here. We're going to talk about that a little bit later. But everything below this this threshold value is considered safe. So you can see we've got one value that's above here. We've got one in the in the transverse direction that's pretty much right there, and then this one here in the vertical direction is below. So you can see each one of these records a little bit different. The magnitude of one direction may be larger than another direction. Here we've got another waveform trace. This is pretty consistent with what we would see with pile driving. So we've got our 0.25 inches per second. It kind of hit it right here at this trace on the longitudinal direction. The longitudinal direction, that's the direction towards the vibration source. So it makes sense, that those surface waves, those Rayleigh waves that I mentioned before that have the highest energy transfer, the longitudinal direction, it's going to pick that up. It's going to pick that up first, and it's going to have the highest magnitude. So that all makes sense. We've got hammer blows about every, 1.5 or 1.25 seconds or so. After the initial hammer blow, it looks like it stayed above 0.25 inches per second. So there's probably another waveform record after this one. And again, this was probably beginning of drive, maybe the first 6 or 8 hammer blows. Again, looking over here on the right, we see these kind of self-tests after that waveform mode was completed. All of these geophones look like they're in pretty good shape. So something else we can do with this waveform data is we can analyze it. We can use fast Fourier transformation to analyze these events. We can, and what it does, it analyzes the event over the full 5 seconds. So we can take, obviously this was not a a transient event, right? This is some kind of sustained event because we can see, well, it's at least lasting more than 5 seconds. But we can see it continues beyond this initial event that triggered it at 0.25 inches per second. This was vibratory sheet pile installation, by the way. So again, we can kind of analyze this event, take a certain area of it, use some fast Fourier transformation, and we can figure out what the dominant frequency was. And this is one of the tools that we use to kind of analyze what caused this vibration. What is this from? What's the source of it? So knowing that there's sheet pile installation going on at this particular project, also having the specifications of the vibratory head handy, having those, knowing that vibratory head operates at that vibratory hammer operates at about 1900 vibrations per minute. Here we can see what the dominant frequency was in the previous waveform event. That dominant frequency is about 32 hertz. Well, we take 32 hertz cycles per second, we multiply that by 60, we get just over 1900 vibrations per minute. So it makes sense. We know what this vibration, we know what's causing this vibration. We know it's this vibratory hammer. We've got a timestamp on the record. We know that at the time this was recorded, they were installing sheet piles. Everything adds up. It all makes sense. Something interesting to note here, we do have some resonant frequencies over here at about twice the dominant frequency at about 64 hertz. If this frequency went out, beyond 90 hertz, we'd probably see another little bump out there for another resonant frequency. So this is a waveform that woke me up in the middle of the night, about 1 o'clock in the morning. I got a notification on my phone and by email that threshold was reached on one of our projects. It was in an urban area, so my first thought was, somebody's vandalizing this seismograph, or they're trying to steal it or something like that. But taking a look at this waveform event, knowing that we set a trigger at 0.25 inches per second, looking at this scale, it doesn't look like anything really got up to 0.25 inches per second. So we're going to do a little bit of analysis, check and see what's going on here. Here's our FFT, and we see that dominant frequency right at 60 hertz, exactly 60 hertz. We think to ourselves, all right, 60 hertz, that number sounds familiar. What operates at 60 hertz? Well, AC electricity operates at 60 hertz, or at least here in the US it does. This particular seismograph was plugged into the wall for a power source. As I said, it was an urban area, very, very old neighborhood. And the wiring was pretty old. It wasn't old knob and tube wiring, but it was pretty old. And I zoomed in on the vertical the vertical component, and you can just barely see right here at 0.25 inches per second. Basically, it was an instantaneous spike. Obviously, that's not a physical occurrence, that didn't, there was no physical movement that was involved with that. So again, being able to analyze this waveform data, it really helps out a lot. We can tell, this obviously was kind of an anomalous event, and wasn't related to pile driving or sheet pile installation or something like that. And I was able to go back to bed. Here we've got another waveform data or waveform trace. This one's kind of all over the place. Let's take a look at our scale here, and wow, our scale isn't 0.4 inches per second, plus or minus 0.4. It's plus or minus 4 inches per second. So the amplitude of this vibration up here is pretty significant. Here, in the vertical direction, we don't really have hardly anything. We got a little bit of noise here and there, but not a whole lot of movement going on. And then over here, looking at our geophone after the event was recorded, and we got something goofed up with our geophone here. Our vertical plane is all messed up, and our longitudinal plane really doesn't look all that good either. Transverse plane looks okay. So it turns out what happened on this one is the geophone was basically jerked out of place, and that's why you get these wild really large amplitude spikes, and it was kind of jerked in the horizontal direction. So that's why there really wasn't a whole lot of vertical motion going on. It was kind of skidding across the floor. This was actually on a floor slab. So again, having this waveform data to be able to look at and analyze is a pretty good tool. Otherwise, if we were just recording in histogram mode, we would see a large spike, see large peak particle velocities, but we wouldn't be able to tell exactly what was going on. Having those waveform events helps us to analyze the event. So we'll talk a little bit about specifications and industry standards. There's a whole bunch of them out there. AASHTO's got some standards. There's some German standards, a couple of different British standards. One of them I think is specific to pile driving. The other is for building structures. Swiss standards, Office of Surface Mining Reclamation, that's a U.S. standard. U.S. Bureau of Mines. That's one that I think a lot of people are familiar with. New York State DOT uses that RI 8507. I think RI stands for Research Initiative or something like that. And there's a whole bunch of other ones, probably a dozen, maybe more. And there's no one size fits all standard. So you really can't, you really shouldn't just apply one standard and, just kind of cherry pick standards here and there. They're all a little bit different. Here we see some of the different standards. I think these are all foreign standards. I don't think any of the U.S. standards are on here. Here's the two UK standards. Here's one up here. Here's one here. A Eurocode, Australia, France, Austria, Finland, Switzerland. But you can see they all kind of have like a little stair-step characteristic shape to them. And there's a reason for that. Something I want to point out, most of the time, so the stair-step that we're used to seeing, that's the RI 8507, the U.S. Bureau of Mines, that scale, the frequency and peak particle velocity scale on that standard is in logarithmic form, both on the X and Y axis. This is not. This is just straight linear. But regardless, we still see that stair-step characteristic shape. And basically that's implying that safe peak particle velocities are a function of frequency. So here we'll talk a little bit about that RI 8507 U.S. Bureau of Mines document, or at least what went into the research for that document. This image on the right, by the way, this is the image of that geophone jerk where it skidded across the ground. We see longitudinal and transverse points on here, but we don't see a whole lot of those vertical points again because it was kind of moved in the horizontal direction. But you can see some of these definitely exceeded what would be considered this safe level, which is this stair step right here. Some people call this the Z curve. I've heard it called the Siskind curve because Siskind was one of the researchers for the U.S. Bureau of Mines. So this was all, this RI 8507, it was all based on responses to ground-borne vibrations. So this whole study, for the most part, was based on ground-borne vibrations. The study was done on 1- and 2-story residential structures. So it was all residential structures, wood frame construction, some drywall, some plaster. That's the reason for these 2 dotted lines. This lower dotted line here is the plaster threshold. Strain gauges were set up throughout the structures. Geophones, for the most part, were outside. And they noticed that there was much higher strain in the structure at lower frequencies. So that's why we see that stair step. You know, that's why the threshold levels are a function of frequency. Higher frequencies, you get lower strains, so you can get higher. You're allowed higher peak particle velocities. But this stair step line, the stair step curve, was basically established based on 95% probability of there being no superficial cracking or you know, essentially cosmetic damage. So the idea here is everything that's going to be below the line, for the most part, if it's below the line, there's a 95% chance that there's no superficial damage to the structure. This does account for the human response to a certain extent, mainly in some of these really low frequencies. But it's more related to the structures. New York State DOT specifications, they reference RI 8507. The specifications 634, 9901, 9902, they kind of go together. That's the one that talks about a building condition survey involving a bunch of, you know, some photographic documentation, interior and exterior of the structure, and identifying the extent and location of any kind of distress, you know, as part of the building condition survey. The DOT specifications do require that the condition survey be performed by a New York State licensed PE. In the vibration monitoring portion of the specification, they state that vibration monitoring should be done when prudent. So obviously there's a little bit of, it's kind of a gray area there, right? It's kind of subjective. Typically, if they reference if they're referencing the specification, then they're going to require vibration monitoring to be done. The DOT in those specifications, their vibration limit is based on that RI 8507 document, which is seen there in the right. That's in metric form. The other thing that the DOT specifications require is a vibration monitoring plan, which essentially identifies, you know, what's being done, what type of equipment is being used, you know, and things like that. We'll talk a little bit more about vibration monitoring plans. Building condition surveys, pictures, lots and lots of pictures. Let the pictures tell the story. You know, take pictures when you're walking into a room, you know, all around the room, zooming in on only the bad areas or only those areas where you've got, you know, cracks coming out of, you know, around window or door openings or something like that, without having a context of that crack. You know, just zooming in on those cracks and those features. You know, there's value to it, but there's not a lot of value to it. You really got to get a lot of pictures, you know, to kind of tell the story. A good building condition survey, people that do it, they're very methodical, they're very organized, they take really good field notes, and the pictures are well organized also. But I can't overstress the importance of taking lots and lots of pictures. I mean, these days 20 years ago when we were doing condition surveys, digital cameras weren't nearly as popular. They weren't nearly as good in resolution. Nowadays you got 12, 15, 20 megapixel cameras, and you can really zoom in and see the full extent of cracks and surface defects and stuff like that. So pictures are extremely important. Here's a picture. This one's a little bit unique. Obviously, we've got a pretty big crack right there. That crack. We've got displacement in 3 different planes. We've got vertical displacement, obviously, and then we've got 2 different planes of horizontal displacement. So being able to note that, being able to measure that is pretty important. Here we've got a crack, at the edge of a of a roof beam or roof joist. Obviously, that's important. We want to document conditions like that. Cracks in walls, CMU walls, measure the magnitude. If you can, put one of these crack comparator gauges up there, take a picture of it. And what I like to do is I like to put a line across there so I can go back to that particular location and say, okay, on this date, and a lot of times I'll put my initials and a date on there. On this date, the crack was 3.5 millimeters in width or something like that. But these are the kind of things that we certainly want to see documented really well in a condition survey report. So some final considerations. I mentioned the vibration monitoring plan. Very important. You want to identify the equipment, not just the equipment being used on the project, vibratory hammer for sheet piles or, a diesel hammer or something like that for, the H piles being driven, on abutments or foundation or something like that. But also the monitoring equipment. What type of monitoring equipment are you going to use? How are you going to set it up? Where are you going to set it up? You're going to record in histogram mode. What's your recording interval going to be? Maybe it's histogram combo mode. What are your alerts and action limits? When are those notifications going to go out? When are you going to start sounding the alarm, right? When do you need to turn down the energy on the hammer, or maybe not put as much downward force on those sheet piles as they're going in. Pre-construction survey, lots of value in the pre-construction survey, and even just with property owners knowing and seeing that there's somebody going around documenting the condition of their structure, they're going to think twice about calling and saying, hey, you cracked my foundation or something like that. They'll think, I wonder, maybe that crack was already there. 9 times out of 10, when we've had people call us up, we've been able to produce pictures before any of the work started that identified some of the defects that they were claiming that some of the contractors had done. In part of the vibration monitoring plan, maybe you got some mitigation methods. I talked about a couple of them. Maybe turning the hammer down. Maybe you're pre-drilling some of the holes for your piles. To maybe intercept that rally wave, that surface wave. Maybe you're digging a 4-foot trench or something around a critical structure that you don't want a lot of vibration, getting to that structure, digging that trench, again, maybe the idea is to kind of intercept those surface waves, those rally waves a little bit. And the last thing, don't get complacent, especially when you've got a lot of alerts going off, maybe the alerts going off 4 or 5 times a day. Take a look at each one of those alerts. Make sure that you can identify what's going on. Is it a transient event? Is it an anomaly? If you don't, that one event that you don't take a look at, that you don't analyze, that property owner, they're going to say, oh, you didn't address this one, or nobody took a look at this one. That's the one that may have caused caused some issues. So just don't get complacent. Make sure that the vibration monitoring, the vibration monitoring plan. It's all part of a risk management program. So make sure that it's not just a 3-ring binder that's taking up space on the corner of a desk. Okay, we're going to get into some questions now. Question number 1.
In the interest of time, there's a few questions here. The first one being, is there a damage threshold for underground utilities?
That's typically up to the utility owner. But I will say that National Grid, their standard threshold is 2 inches per second. And that's somewhat consistent with a lot of the other utility companies. So we'll go through these questions quickly. Question 1, of the 3 main wave types, compression, shear, and rally wave, which one has the highest energy transfer? That is rally wave. About 2/3 of the energy is transferred through the rally wave or through the surface wave. Question number 2.
Steve, next question. Who determines the number and location of monitoring points?
The number and location of monitoring points a lot of times is part of the project specifications. They may specify 3 monitoring points. They may have general locations, and there may be a note in there that says these are general locations subject to change based on field conditions. A lot of times these seismographs, these monitoring points, they do move around based on the type of work that's being performed and the phase of work. So true or false, structures are more sensitive to vibrations than humans. False, humans are more sensitive to vibrations and excellent vibration receptors. Question number 3. True or false, transient events are greater than 60 seconds.
Next question, Steve. Have you ever had to perform vibration monitoring caused by human traffic within a building to conform to design requirements, namely elevated floor systems?
Yeah, we've been asked to do that a couple of times. Those vibrations are a lot more sensitive, again, because humans are more sensitive to vibrations than structures. The type of equipment that we have is really geared more towards construction vibrations, so it really doesn't have the sensitivity that you would need to measure something like that, nor does it have the sensitivity to measure vibrations for like MRI equipment, X-ray equipment, things like that. Those are very, very sensitive pieces of equipment, and the equipment that we have and the equipment that we use, it just doesn't have that sensitivity. Transient events are greater than 60 seconds. That's false. Question number 4.
Steve, last question. With so many different vibration specifications, who determines the appropriate vibration specification for a project, and how is that determined?
Yeah, that's a good question. A lot of times the specifications will, like the DOT specifications, they reference the RI 8507 from US Bureau of Mines. Some of them will provide just a peak particle velocity threshold, say, 0.5 inches per second or 1 inch per second, regardless of what the frequency is. Some project specifications require that a contractor hire a vibration specialist like ATL to go out, evaluate the structures, how close is the structure to the work being done, what type of work is being done, and then based on the information we see out in the field, the equipment that's being used, how close or how far, we can come up with, or a vibration specialist can come up with the appropriate threshold values. True or false, high frequencies cause higher strain. That's false. Lower frequencies cause more strain. And last question, true or false, vibration limitations are typically a function of frequency and particle velocity. That answer is true. That's the reason for that that stair step nature in the in those vibration threshold documents or charts. Went a little bit over. We got any more questions, Howard, or did we address all of them?
No, there are no more questions, Steve.
Okay, thank you everyone for, I'd like to thank everyone for their time.